everyone. I think the time is up, so we will going to start our this fight. And at the beginning, I have to notice each participant. You cannot use. You are not allowed to use internet, and you cannot take any picture or any videos in the fight. Okay. And please don't put anything in front of the projector, and in case to damage the projector. Okay. So at the first, I will introduce our juries. And the first one is Professor Su Jiongwu from GIA University. And Professor Guo Zhelai from Senegal. And Professor Hu Shufen from Taiwan Normal University. And Professor Lu Tinghua from Taiwan Normal University. And I'm Lu Zhenliang from Kaohsiung Senior High School. Okay, and please each team leader to introduce your teammate. I think the reporter first.
Hello everyone, we are Team Mingdao Mei. I'm from Mingdao High School. And this is Jerry Tao, Ray Cool, Derek Wu, Emily Lin, and I'm Robert Lin. Thank you.
Okay, and then opponent.
I'm the leader of Team Choco Team Jiao, and this is Lin Xide, and this is Chen Shiwen, and Chen You, Liao Zhijian. Thank you.
Okay, thank you. And the reviewer.
Hello, viewers and fellow competitors. I'm the captain of Team CYJ, and my name is Chen Yujing. This is Lin Heozhen, Lin Richard, Wu Weizhong, Chen Bowei, and we are come from Bongting Senior High School.
Okay, we will start the first round. Please write down the reporter and the opponent and the reviewer on the blackboard in the start counting. start your report.
Good afternoon, honorable judges, my competitors, and my partners. Today, I'm going to present problem number 12, rice kettlebells. Here's our problem statement. Take a vessel and pour some granular material into it, for example, the rice. If you dip a spoon into it, then at a certain depth of immersion, you can lift the vessel and contents by holding a spoon. Explain this phenomenon and explore the relevant parameters of a system. Our main focus should be the relation between the depths and the maximum static friction. Also, the relation between the diameters of the vessels and maximum static friction. And third would be the relation between the diameter of the silicon dioxide, which we use as our granular material, and maximum static friction. And here's a demonstration video. So at first we press the silicon dioxide and then press the rod inside. And after it reaches the depth we want, and we press the silicon dioxide by another vessel with a hole under it again, and to lift the system up until the system breaks. And here's our experimental setup and equipment. We use the material PLA as the material of the rod in the vessel, which we printed by the 3D printers. And we use silicon dioxide as our granular material. Here's our fourth diagram. The FA and FB indicates the static friction between the rod and the silicon dioxide. And the FC and D indicates the static friction between the silicon dioxide and the vessel. If we see the diagram by the view of this rod, we can find out that F equals to the gravity of a rod plus the FA. But if we see the diagram by the views of a vessel, the FA will equals to the gravity of vessel and silicon dioxide. So we can find out that F equals to the whole gravity, the gravity of the whole system. And here's our phenomena explanation. So we define the vessel and the silicon dioxide are the sun system, since we would observe this phenomenon by the view of the rod. So the FC and FD can be referred as the inner force. So also, according to the force diagram, the F provides a force to lift the system up. And if the F is little than the gravity of the whole system, the system can't be lifted up. But if the F is bigger than the maximum static friction, the system can be lifted up. So it means that we wouldn't get the value that is bigger than the maximum static friction. Here's our theory. The normal force equals to the pressure that works on the contact area. And then we integral this equation, and it would be like this. And why are we dividing the K? K means the conversion coefficient, which indicates the tightness of the granular material. And the maximum static friction will be the mu s 2 times the normal force. Here comes our experiment. Here's our experimental methods. First, to pour the silicon dioxide in a vessel and press it to a tight situation to control our initial condition. Second, we use a hammer to strike the rod in and press the silicon dioxide, and it also because we want to control its condition. Third, we use a vessel with a hole to press the silicon dioxide. Fourth, we use a cotton thread to link the force sensor and pull it, and then we will get the value of the maximum static friction. Fifth, if we can't lift the whole system up, then we can get a maximum static friction. But if it can't be lifted up, we will keep applying the force until the system breaks, which means that we can't lift the whole system up. So in this case, we can get the gravity of the whole system and the maximum static friction. And here's an analysis method. We use Pascal as our analyzing application, but the only part we will use is the force part. And the part that is circled indicates the maximum static friction. here's our prerequisites. The diameter of a rod is 1 centimeter, and the diameter of the vessel is 3, 4 to 7 centimeters. And the diameter of the silicon dioxide is 1, 1.5, and 3 millimeters. And the density of the silicon dioxide is 1,600 kilograms per m squared. And here's the coefficient of static friction between the different diameters of the silicon dioxide and the vessel. So there are like about 0.61 to 0.71. Oh, here comes our experiment 1. We will change the depth of a rod. So we're going to find out the relation between the depth of a rod and the maximum static friction. And the diameters of silicon dioxide and the vessel we use will be 3 millimeters and 3 centimeters. And our hypothesis is that the depth of a rod is positively correlated with the maximum static friction. And here's the result. So according to our graph, we can find out that depth of a rod is positively correlated with the maximum static friction, which fits our hypothesis. And if we analyze the graph as 3 parts, if we divide it as 3 parts, the A part indicates that we can lift the system since the force is bigger than the maximum static friction. And the B part means that we can lift the system because the force is smaller than the gravity of the system. And the blue dots is the experimental value of the maximum static friction. And the gray dots is the experimental value of the gravity of a whole system. So we can find out that in the C part is the part that we can lift the system. So we can infer that the area of C can indicate the difficulty of pulling the system. Here's our experiment 2. We will change the diameter of a vessel, which is 3 to 7 centimeters, and to find out the relation between it and the maximum static friction. And our hypothesis is that the diameter of a vessel is negatively correlated with the maximum static friction. So in this graph, we can find out that our experimental value does fit the theoretical value, and as the diameters of the vessels increases, the K will be bigger, which means that the maximum static friction will be smaller, since we divided the K in our theory. So the same trend would indicate at the diameters of 5, 6, and 7. So we can find out that when the diameter of a vessel is smaller, the curvature is bigger. So it means that it can lift a bigger weight. And also, the C part is smaller as the diameter increases because it was influenced by K, since the K would be bigger as the diameter increases. The experiment 3 would be that we would change the diameters of a silicon dioxide, which is 1.5 and 3 millimeters. And we're going to find out the relation between it and maximum static friction. And our hypothesis is that the diameter of a silicon dioxide is negatively correlated with the maximum static friction. And here's the result. So as the diameter of a silicon dioxide increases, the K will be bigger, which means that C will be smaller. Also, the same trend indicates at the diameters of 4 centimeters. So we can find that since the K is bigger, the maximum static friction would be smaller. And this is from our experimental value, we can find out that same trend indicates on the diameter of 5, 6, and 7. So we can conclude that in different values of vessels, as the diameter of silicon dioxide increases, the K will be bigger, and the C will be smaller, and the maximum static friction will be smaller either. And the difference between the line of 3 millimeter, the silicon dioxide is bigger, so the range of K will be bigger. And here comes the discussion. This graph indicates that if we change the tightness between different diameters of the vessels, and the delta x indicates the influence of the rod when we insert in, and the delta A max and delta B max is the maximum compact length. As delta A max is smaller than delta B max, if the delta x divided these two values, we can find out that the smaller diameter is tighter. So the K of smaller diameter will become smaller. So we can infer that the maximum static friction of smaller diameter is bigger. And this graph indicates that the maximum static friction of different diameters of the vessel, of the silicon dioxides. So as well, the delta x means the influence of a rod. So we can infer that the maximum static friction of smaller diameter will be bigger. Last but not least is our conclusion. First of all, the depth of a rod is positively correlated with the maximum static friction. And second is that diameters of a vessel is negatively correlated with the maximum static friction. And the third is that the diameters of a silicon dioxide is negatively correlated with the maximum static friction. Which these three is what we got from our experimental values. And the fourth is the area of C can indicate the difficulty of pulling the system. Fifth is that the value of K is related to the diameters of a vessel and the silicon dioxide, which I mentioned in my discussion. And this is the end of our report. Thank you.
Okay. So the question of opponent.
In your observation video, we see you place the rice in a vessel, and how should you place it to make sure every time the place is the same?
So we press as tight as we can, so to control the initial condition. Initial, like the first statement. First statement, like if yes, initial, the first.
Okay. So how about, have you ever tried to down the friction of the vessel?
What do you mean down the? What do you mean down the friction of a vessel? Can you repeat your question?
Just like you talk about the friction between the rod and the rice.
Yes.
Have you ever done the friction between the rice and the vessel, just like change the texture of the vessel?
Oh, since we observe this phenomenon by the view of a rod, so what I just say in this, we define the vessel and the silicon dioxide are the same system. So the force between it can be the inner force.
And our next question is, have you ever done, because
Yes.
the values you have done in your experiment was all static frictions. Have you ever tried to down the kinetic when the rod is full of the vessel inside it full of the rice?
So can you repeat your question?
Just
Like, the maximum static friction is a critical value. So we find the critical value, but I can't find the kinetic friction.
Okay, time's up. You have prepare for the question, opponent take vote. 3 minutes. Okay, thumbs up. The opponent takes the floor.
I'm the opponent from Team Triple T, and I'm going to oppose the number 12 problem rice kettlebells. And this is the problem statement. The problem statement is that take a vessel and pour some granular material into it. For example, rice. If you dip, example, a spoon into it, then at a certain depth of immersion, you can dip the vessel and contents by holding a spoon. Explain this phenomenon and explore the relevant parameters of the system. So here is the pros and cons to the proposal. The pros of the observation video is that he clearly shows the phenomenon and he explains the phenomenon. And the cons is that he priced it by pricing using his hand. And the parameter discussion. Pros is that complete parameter discussion and the clear explanation. And the next theory, the pros is that he discusses parameter theory and their explanation, which he has done in his experiment. And the next is that the cons is that he leads through explanation of formulas indicating with diagram. And for the experiment part, the pros is that the graphs show qualitative result clearly, and the cons is that no quantitative analysis of data, and that he failed to explain graph comparing with the theory, and failed to confirm experiments using theories. So here is my question. Can I skip this?
Discussion.
Yes.
For my first question, in your observation video, you put the vessel using your hand, and
Yes.
do you think this will affect your experiment or?
I think no, since it is vertical, the first chain, the vessel in my hand. So using my hand is only I will slowly pull the vessel since I want to control. Since I don't want to give it a big acceleration, and also if I use hand is only used to apply the force, since I'm going to find the maximum static friction.
But you use your hand to pull, it may increase the force to the rod, so the friction might be increased.
Can I please use this? Like, so this is the first sensor,
Yes.
and this is a vessel, just like maybe the rod, like this. So I use my hand to apply the force right here, and it is parallel to.
But when your hand is holding, it might be forced into like this.
No, but the vessel wouldn't have the change of the shape, like because it's the vessel is like this. So if you press it, it wouldn't give it any and also
Your container is hard.
it's hard enough, and this is 0.3 centimeters. So I think it's enough. So if you
Okay. How can you confirm every time you put the rod into it is vertical?
Vertical? Oh, you mean the same?
Yes, vertical to the vessel.
Actually, I cannot say that it's 100% vertical, but I would try. And like, oh, this one didn't have the mark, or in another vessel, I have the mark. If this is the top view of the vessel, I have the mark this. So it's better for me to find the middle.
And how can you, when the rod is inside it, how can you make sure every time it is vertical? Because it might be affect the result of a
So like because it's a rod, if I know that the angle, this one, the rod and the surface of the granular material, I will know the angle inside since it's just like this. So it's parallel. So if a rod is like this, and I will know the angle right here, then I will know the angle right here.
Okay. How about in your experiment? The problem statement says right, example right, and the reason why you use the silicone dioxide. Can you tell me?
Because the problem statement says it's the granular material, but it isn't limited to the rice, since it's the granular material. For example, rice. And in my experiment, I think that because the shape of the rice is like this, and if I use silicon dioxide, its size would like this. So it would be more precise, and I can define it as a more ideal model.
Have you ever tried to make the rice into this shape? Just like
You mean to make the rice into a round shape?
yeah.
No, because I think the shape, if I make it to like this, it will only affect the coefficient of static friction and kinetic friction also.
So you don't think the friction of the rice surface isn't a parameter?
It is a parameter. So I use the round thing, since if it's the oral thing, maybe it's arrangement with like this. Then you don't know the force between it. But if I use something if I find this as a circle, and maybe perhaps this arrangement would be like this, it is better to say that it's the ideal model.
But in your theoretical calculus, I see you use the pressure, which is the formula for the liquid, and in my opinion, I think there might still be another different state of even though a sphere. So how can you explain it?
Can you make your question again?
I mean, for my first question, I think even though it is a sphere, I think there will still another state type of it. So
You mean why can I use this formula?
I mean, it's still not that formal to this. It might be like this or another. How can you make sure every one of these is like remarkable?
To be honest, I cannot say that it would be like this. But if it's relatively compared to the rice, and if this is a side view of a vessel, so if a rice is oral, so it might be like this. But actually the arrangement might not be that. So if it is oral thing, it might be like this. And in a firm view, it might be like a circle or what. So compared to the oral size, I think the ground size would be a more ideal model.
So you consider this is experiment
And
error or
no, and also in my demonstration video or my experimental methods, I have mentioned that I do press it. So I would try to make it into the densest condition, so to control its initial condition, so as to minus the error.
Okay.
Yes.
My next question is, how can you use liquid pressure formula in your model? Because this is still a particle, not a liquid.
For this question, actually I have calculate like if I this is the initial condition of a vessel, and if I insert the rod in, there might be the delta. If this is delta, then there might be changes of depth, right? And I do calculate the volume of this, and this is approximately equals to the volume of this. So I think it can be used. It can use this formula, the liquid one.
How about when you put it, because you say there will be a delta H over here, and will this delta H affect the friction of the rice or affect your experimental results?
So, like when I insert the rod, the delta H would be bigger, right? So, but as I do mark the lines on it. So when I insert it, the delta H would be bigger. So the depth of my experiment will be can be controlled.
How about the energy losing if you insert the rod into the rice?
Why do you think there will be the energy loss?
So you think there, I mean, okay.
So actually, I think there will be the energy loss. Can you last one, the conclusion? Down. Thank you. So I think this one could be explained by this force chain. So this is the initial condition of the vessel, and if I insert in, it would affect the area of right here, and I would draw the rest. So the first one would be like this, and now if I lift a rod up, the force chain will try hard to this, and if it reaches the vertical if it's like it is 90%, and it would reaches the maximum saturation, and if the force chain like this, and the system will break, which means that the rod can like this, and it can lift the whole vessel up.
So in your model, you say there will be the material will be like this, and how can you make sure it will not affect the equipment?
Because we do have precedent.
Oh, so after you insert it, you have
Yes.
still present again.
Demonstration.
Okay.
Yes.
How can you make sure every time this will happen?
You mean the conditions of every time will be the same?
Yeah.
Yes. So I press it. If I didn't press it, the density would maybe like this, or next time maybe like this. So when I press it, the force chain would go down, and it will go down, and it finally reaches the same condition.
Okay. I have no another question.
Okay. So the next stage is opponents summarize the discussion for 1 minute.
So we have talking about a lot of theoretical discussion. and just like the one we had, because he didn't mention in his presentation for a lot of the reason why he used the formula or why he used the material for his improvement. So we have talking about a lot of about it for the discussion, and I have asked him about, do you think the vessel, the friction of the vessel will be a parameter? And he says no, because he thinks that is inertial force. And I have asked him about when he pull the vessel with his hand, will it affect his experimental result? And he has answered me that no, because he thinks
Okay,
that
okay. So the next stage is question of the reviewer to opponent and the reporter. 3 minutes.
Thanks to the reporter and the opponent's presentation, there are some questions I would like to ask for the first. And first, for your variable one, you changed the depth of the rod, right?
Yes.
And you said in your conclusion, you said that when the depth and the rod has the positive correlation between the maximum static friction, right?
Yes.
How to explain this phenomenon?
So we integral the project that the silicon dioxide works on the contact area. So you can say, you know that if a depth becomes bigger, the contact area will become bigger. So this is how I.
Okay. How about the opponent's opinion?
Can you say that again?
Okay, for his the reporter's parameter one, he said that when the depth of the rod has the positive correlation between and of the maximum static friction, and how to explain this phenomenon from his results.
Because I think it might be because when the depth is large and the pressure of the rice will be increased, so the friction will increase. I think it might.
Okay, and my next question I would like to, and reporter, and from your variable 1 and 2, you said the diameter of the vessel and the silicon dioxide has the negative correlation between the maximum static friction, right?
Yes.
And how to use principle to explain this results?
Do you mean using my formula?
Yeah, your formula.
So I just say that changing the vessel is like changing its K, because its K is bigger.
Yes.
And in our sorry,
Why the K is bigger?
K means the tightness. So
Okay, sorry.
this one right here. I did explain this.
Okay, so because of the pressure, I will put
The tightness.
Okay, and how about the opponent's opinion about his explanation? Do you agree with him, or do you have your own opinion?
I think it might be, so I agree with him.
Okay, and here's all my questions. Thank you.
Thank you.
Preparation of the reviewer for 2 minutes. Okay, time's up. The reviewer takes the floor for 4 minutes.
Okay, honorable judges, the competitor and the reviewer from CYG, and my name is Ho Wei Chen, and today I'm going to review problem number 12, rice kettlebells. And here's the problem statement. Take a vessel and pour some granular material into it. For example, rice, or if you dip a spoon into it at a certain height of the immersion, you can lift a vessel and content by holding the spoon, experience the phenomenon, and explore the relevant parameter of the system. And here's the reporter's main focus. And here's how depth affects the maximum static friction, and how diameter of the vessel affects the maximum static friction. And for a summary and comment of the reporter, and he used two theories. First is the gravity and the friction to describe the motion. And for his parameters of his experiments, and one is the depth of the rod, and another is the diameter of the vessel, and the other is the diameter of the silicon dioxide. And for his conclusion, the depth and the maximum static friction are positive correlation, and the diameter of the vessel and maximum static is negative correlation. And the diameter of the silicon dioxide and the maximum static friction has negative correlation, and the rod will not be pulled out because of the static friction. And for advantage for the report, he has full time control and enough amounts of charts and describe the theory clearly. But for suggestion, I suggest him to answer opponent's question more accurately and explain the principle more clearly. And I think it has lack of parameters. And for a summary and the comments of the opponents, I suggest for advantage, he has specific and important questions and describe the question clearly. But for suggestion, I think he too focused on the theory parts. For a summary and comment of the discussion, the first question, opponent asks reporter did the method to put rod affect the results. The reporter said that put it vertically, and a reviewer thinks that reporter should explain more clearly. And the next question, opponents ask how to confirm the rod is vertical every time. And reporter said it doesn't affect the result lots. And reviewer thinks the reporter could use some methods to check it in the experiments. And the next question, have you considered to use other shape rice? And the reporter said it didn't consider it. A reviewer thinks the reporter could use some methods to check it in the experiment, for example, like force chain. And for my reviewer's first question, I asked the reporter how to explain variable one results. And a reporter said because of the pressure, and opponents agree with the reporter. And to my opinion, I think they could use the force chain to explain it in other way, but I think their explanation is also well. And for another question, I guess do you think all the rice be analyzed like a model? And reporter said because of the tightness, and opponent agrees with the reporter. I think its explanation is very well. Thanks for your attention. It's all my presentation.
Okay, thank you. Concluding remarks of the reporter for 2 minutes.
Okay, thank you for the opponent and the reviewer. Okay, during our discussion, first of all, the reporter has actually compared data to our experiments, and we mentioned that it fits quite well. Second, we discussed about the experimental status, and we have tried our best and marked the vessel to ensure the initial condition, and we appreciate the opponent's suggestion. Also, we think there's probably energy loss in the system, and we press the rice back after inserting the rice to increase precision. And the energy loss is during the first chain. So we are going. So we press the rice is to ensure the initial condition of this vertical. Yes. And first, since the silicon dioxide is strong, so the reviewer thinks, so the reporter thinks it's closer to ideal model. And about the mass is that I think we can use the equation of the liquid since although the density changes, the mass doesn't change. And this is the aim of my concluding remarks. Thank you.
Okay, thank you. Well, the question of jury for 5 minutes. Any question? Okay.
I have a question for reporter. You consider the wrong silicon dioxide. What if you consider different shape of the granular particle? If you take the consider it into elliptical shape,
You mean the shape is not drawn?
yes. How does it affect your data?
I think the data would be unstable since if it's like maybe oral, if it's oral, oval, the side view of it, if it's ideal, things it will be like this is it. But in fact, the arrangement of it might be like this. So the front view of it might be a circle. So it's hard for us to be precise. And also we may not use our
Briefly answer. Does it affect your results?
Yes.
Okay, it will increase or decrease the friction.
It depends on its arrangements.
Okay, how about Onan?
I think it might affect the result, but I think the reporter might show the data what he does to show us and predict what is the reason of what will it change the result. So I think it will.
And I think we could use force change to describe this principle. And I think although the particle is not an ideal model, but it could also be counted into a result by using force change to predict its change of the motion or the static friction.
Can I make myself more clear? Why did I say it depends on the arrangement? Since is that if it's not circle, we cannot predict that the contact area will be bigger or smaller. But and also if it's oral, maybe the force chain, the convey of a force chain would be smaller and the energy loss would be smaller. So I cannot predict that it would be precise. Yes.
Okay.
Any question?
I have a question mainly for the reviewer. What is the force chain that you?
So I use the breadboard to describe it.
Can you be sure?
For example, if we supply a container just like this, and if we put many balls or particle in this just like this, and then are set with each other and attached with each other, and so it has the transmission of the force, and it could be expressed just like the force, just like for example, if the pressure here is more like that, and you will transmission like this or other pattern. And for our opinion, the time mass of the force could change the.
No, that's enough. I only need one is here that force chain. Thank you.
Okay. Any question?
Follow the Professor Ruth's comment. Your silicon dioxide is a glass ball, right?
It's not glass ball. It's it's the material to become a glass ball, but the actual thing is it looks like the salt.
Same, right? It's not round shape.
Yes, but yes,
The shape is all the same and it's like ball, right?
yes.
But you say it's a silicon dioxide. I know silicon dioxide is glass. So the surface is sharp or it's very smooth
Oh.
or it's rough.
Oh.
Because it will
but I believe that even that yes, compared to the rice, it would be it would be more it would have more shot, but
Can you show?
I know this is a parameter that we didn't take account.
So if it's a silicon dioxide, it should be like a glass ball. So if you compare with the rice.
It's not if it's a lot of silicon dioxide, it would be a glass ball, but actually if I say it just looks like salt or sugar, like the shape. Yes.
So it's not that ball.
Sand is also silicon dioxide, right?
Yeah.
So it doesn't mean that silicon dioxide does not mean glass.
Yes.
Okay.
And we agree that the coefficient of friction
Yeah, so okay, so you want not glass and even not sand. So what the material is your granular particles? It's just only brief answer, okay?
SiO2.
It's out to, yeah, so what's
the
what's
chemical
the,
component?
yeah. So, oh, it's okay, yeah. Yeah, I think time is up, yeah, okay, thank you. Yeah, so please, calculate the score. So now we will show, would you please show the score of the reporter? The score is 5, 7, 7, 7, and 7. And please show the score of opponent. Okay, the score of opponent is 5, 7, 6, 6, and 7. And please show the score of reviewer. The score is 6, 7, 6, 6, and 7. Okay, so that's so we finish this stage. With any comment or no? I think that the score, yeah.
Silicon dioxide is a chemical.
Okay, we will continue to our second round. The problem is the problem form. The regular finger, and please write down the reporter and the opponent and the reviewer's name on the record. And start our timer. Okay, thank you. okay thumbs up. Please start your report.
Okay, so I'm Jiawei from Team Chokoti, and I will be presenting problem number 1, fractal fingers. And so this is my outline for my presentation. So first, I'm going to start with the problem, then I'll show you the observation, and I'll find the reasons and parameters. So we classified it as dynamics and geometry, and then the experiments, and then I'll end with the conclusion. So first is the problem statement. The effect of fractal fingering can be observed if a droplet of an ink alcohol mixture is deposited onto diluted acrylic paint. So the important part here is the ink alcohol mixture and the acrylic paint. So I will discuss how the geometry and dynamics of the fingers being influenced by relevant parameters. So our target is the geometry and dynamics of the fractal fingers. So first is the observation. So we can see in the video that there are 2 stages in the video. So there is one stage that's, before the fingers form, there is a circle expanding outward. And then the second stage is the fingers expanding, so the fingers growing. So we dropped 3 drops during that video, and we can see that the fingers grow outward. So stage 1 is that there's diffusion without any fingers forming. So when there are no fingers formed, but this is a necessary stage to form fingers eventually. And for the velocity of the stage 1, it is slower over time, as you can see in this video here. It gets slower over time. So now stage 2 is that the fingers appear, so the fingers start growing outward. And it becomes more complicated as it grows outward and looking like a curve. And the velocity is very hard to measure since the fingers are fractaling in different tips. So let's look at some more detailed observation. So this is under a microscope, and we can see that the fingers will grow outward in very complex and irregular patterns. So in the video there, that we can put every 4 seconds a picture that eventually shows the growth of the fingers outward. So is our prediction. We predict that it is a positive feedback. So a positive feedback is that a property affects in one way that also changes the property of another thing that increases another effect. So this is a cycle that is positive and increases the effects. So the question is that what's our A, B, and 1, 2? And this is the graph that we will fill out. So how may the parameters influence the phenomenon? And so are the dynamics and the geometry. So first is the Hill-Shaw flow for dynamics. So the Hill-Shaw flow, according to our references, is that it is a flow that is very dominant on its viscous force. So we can conclude with a Reynolds number, which is inertia force over viscous force, that the Hill-Shaw flow is a very small Reynolds number flow. And also, it is a miscible solution. So considering that there are 2 different kinds of, it is a mixture here, considering the ink alcohol and the acrylic here. So the miscible solution also causes even more complexity in the Hill-Shaw flow. So it helps us find the condition. So the effect of the Reynolds number is how the different finger formation is being put out. So how complex it is, we can see it according to the Hill-Shaw. And these 3 are parameters that we will be discussing. So then is the dynamics of the velocity of the finger. So we just said that the stage 1, the velocity decreases. So as time evolves, the velocity in stage 1 decreases, and the velocity of stage 1 and 2 will determine the finger's formation. And we will talk about the quench and the growth of the fingers. So first is the quench and growth. So now the growth is when the finger's velocity is larger than the stage 1's velocity. So we can see here that the fingers will grow outward. And because it is larger than the stage 1's velocity, it will not be caught up by the outer circle of stage 1. And the quench is vice versa, which is when the finger's velocity is smaller than the stage 1's velocity. So we can see here that the light blue line is the growth of stage 1's outer circle. And it's quenched or caught up to some slower fingers that are being formed. And that means that these fingers are being quenched, or they disappear in our observation. So there's a relation between the velocity and geometry. So we can see that in this segment of pictures, we can see that the fingers will grow. And this is the complexity of the finger we will talk about later. So we compared this t equals 0 and t equals 16 picture. So the t equals 0 we edited to make it red, so it will be better to compare. So you can see that the fingers will grow outward, and the complex or larger the fingers, larger flow the fingers have, the more it will grow outward. So we can see here, the larger flow or the width of these fingers initially will cause the fingers to expand or increase in a more complex way than this when the flux or the flow is smaller. So here it's more complicated than this. And so now our prediction is that the longer the finger is, it gets larger velocity causing by flux, which is the width that we see here. So there's more ink to go through, so the flux will get larger and becoming more complicated throughout time. So we can see that the trend is the amount of main fingers will decrease, but it will get more complicated. So now the instability takes place. So when we see the phenomenon from our naked eye, it is seemingly like a continuous line here, but under the microscope we can see that it has jagged patterns throughout the line here. So that means it is very unstable and will grow out from these jagged parts. And so we can conclude that these instability parts will eventually grow out many fingers in many different directions. So it will correspond to the positive feedback mechanism, since it is already complex and it will get even more complex. So now is our experiments. So our setup is like this. We have an acrylic paint dish here, placed below a burette, which we will fill with ink alcohol mixture. And this burette is fixed onto the metal here so that it won't move. And we record the motion of the fingers using the camera put here. And so now we have the side view of our setup. And our general procedure is adding 10 milliliters of pouring acrylic paint. The important part here is that pouring acrylic paint is, it has a tendency to become flat, so we don't have to worry about it being flat or not. So now we set up the device and drop the mixture. And the mixture now is ink to alcohol 1 to 5 to the middle of the dish, and we will record the process and analyze with tracker. So now we will use a microscope and tablet to record our motion. So we can see that throughout the motion, we can calculate the amount of main fingers that we just talked about in our theory. So we predicted that the main fingers will decrease due to the velocity. So when t equals 0, we can see that there are little fingers here, and these are main fingers considering t equals 0 in this image, just in this image. So we can count that there are 57 main fingers now. As time evolves, t equals 4, so the main fingers here will decrease. And how do I define main fingers? It is from the outer circle and the first and the largest width out of the larger circle. So now the same goes for 8, 12, and 16, and 20. So we can see that the number of main fingers decrease over time. And this is due to quenching. So we record the velocity of stage 1, and it decreases over time, as we can see here. And the negative part here is an error due to tracker. So now we can analyze this graph, and the phenomenon shows that the diffusion rate decreases over time. And our explanation is that no fingers are formed because of large real numbers. So now is the recording of stage 2. So since the finger's length is not a constant, we can choose 5 fingers to focus on and observe. So we can see in this graph here that at t equals 0, we can start the fingers right here, and when it grows to here, it grows at the length of d. But because of the outer circle also growing outside, so the actual finger length will change. And then we choose these 5 fingers in this picture right here. So we can analyze the growth of these fingers. So this is finger 1, and 2, and 3, and 4, and 5. The thing here is that these all are a trend of the fingers growing outward. But there is no rule found between the 5 because of very complicated environment. So we can see here that these 5 fingers, why did we choose these 5 fingers? Because the environment here is that this bumps up and then comes down and then bumps up again. And we can't really compare these 5 environments because of this being too complicated. But the fun part here is that 1 and 4 are very close to each other, so we can slightly compare them because of their similar environments. So now if we compare 1 and 4, we can compare that 1 has a width of 0.4 and 4 has a width of 0.17. So these 2 points are what we track on tracker. So this is our main finger of 1 and this is our main finger of 4. And now as time evolves, so the final state is that 1 has been growing a lot and has become this huge finger, and while 4 only grows a little bit to here. So we can conclude that width, which is 0.4 and 0.17, has a great, plays a great part on growing. So flux is a very important parameter, and viscosity also matters. So we can see that water 1-to-1 will not actually diffuse a lot. So we can conclude that larger viscosity difference, the more easily a finger can be formed. A small Reynolds number results in easy formation of fingers, as we talked about in the Gilshaw flow. And longer, wider fingers cause more flux, which is increased length and positive feedback. So this is our
thank you.
conclusion.
Question about opponent, the reporter, 2 minutes.
Okay, so the first question is that do you control the amount of dropping? So each experiment, do you control the amount of dropping?
Yes, we do.
So if you did, how do you control it?
We drop 1 drop.
Can you define the 1 drop?
Because we use a burette here, and we can turn the burette here, and it will drop 1 drop.
Okay.
Yes.
So there's no like a specific like 1 millimeter or 2 millimeter. It's one like.
We view burette as a pretty precise
Okay.
instrument here.
So how is the finger affected by the variables that you did in the experiment?
So
just briefly explain it.
So like for example, viscosity here. The fingers will not grow that much when viscosity is lower when we add water to the acrylic paint that we can see here. So we did an experiment in pure water, but the diffusion barely happened, so we don't have pictures to show.
Okay, so so what, in your opinion, caused the finger?
In my opinion, the fingers are caused by diffusion or like the diffusion gradients, we can say. So this starts to flow outward.
Okay, so do you think that viscosity is the difference of the viscosity between the acrylic paint and the ink alcohol mixture are one of the
viscosity difference between, you mean the ink alcohol and the acrylic?
Yeah.
It will have some effect because of there will be a force to push the fingers outward, but I do think that diffusion here is the main thing that we will see.
Okay, thumbs up. Preparation of opponent, 3 minutes.
Okay, so
okay. Opponent take floor for maximum 4 minutes.
So, honorable juries and the competitors, this is the opponent from Team CYJ. My name is Brian Tu, and today I'm gonna oppose problem number 1, fractal fingers. Okay, so the problem statements are: the effect of fractal fingering can be observed if a droplet of an ink alcohol mixture is deposited onto diluted acrylic paint. How are the geometry and the dynamics of the fingers influenced by relevant parameters? So this is a summary and the comment of the report. The summary, so the phenomenon part, he uses three things to describe it. So the first part is the diffusion, and the second part is the fingering, and the third part is the stop, which I'm gonna talk about, discuss it later. And the theory part, he uses three parts to describe the theory. So the first is the Hill-Shaw flow, and second is the quench and the growth, and third is the instability. So the experiment part, he uses two parameters, the length and the width. So the conclusion are the motion is influenced by viscosity and Reynolds number. So here's some advantages and suggestions I want to get to the reporter. The advantages are he had a well presentation and detailed explanation in the experiment. But the suggestions are maybe he can have more parameters, and he didn't have too much principles or theory. The third are takes a little bit too long to finish his report. Okay, so the discussion part I'm gonna discuss next are, first we can separate it into 4 parts. The observation part we can discuss about diffusion and fingering. And the second part is the theory. Like we can talk about the evaporation or the surface tension. The third part are the experiment, and we can talk about the setups and the parameters. Okay, thank you for listening. And I'm gonna switch to the discussion part.
Okay, start the discussion.
Okay. So first of all, you mentioned that you think there are no theories that can prove, you cannot prove your, in your previous discussion. Yeah, no rule can be found by a complicated environment. So, did you think that did you control the temperature of the
Yes, we control the temperature.
Okay, so how about the humidity?
Yes, we control the humidity.
Okay, so what do you think what caused the complicated environment?
So I just said that the complicated environment here is because this this line here that we can see has a different parts of like, let's say, curvature to it. So we can see that the ink density may not be the same throughout this curvature.
Okay, so your environment doesn't mean that the outside environment is
Yes, the environment inside the dish.
Yeah, I appreciate it. And so can you turn to page 4?
Okay.
Okay, so the observation. You mentioned that there are different stages, right?
Yes.
So can you put it in, into the quantitative explanation about how the stages were? How does each stages have the same time, or just briefly explain it, like the
In my opinion, this observation is a qualitative observation.
quantitative.
Yes, I'm saying that because this is a qualitative observation. So as I define my stage 1 and 2, I can only say that before the fingers are formed and after the fingers are formed.
Okay, so do you think you can predict how would the stage 1 and stage 2 have the different how can you predict the time from each stage?
You can predict how long stage 1 is and how long stage 2 is.
Like differentiate by the parameters that you did, like that. So can you do you think you can predict it in your opinion?
To me, this is a prediction that can only be derived from experiments. I cannot predict it from no experiments.
So do you think that there are so you mentioned that you observed the velocity, you did have the data for the velocity of each stage, right?
Mm-hmm. Yes.
So do you think just briefly explain how the parameters affected the velocity?
When we talked about the Heel-Shaw flow in our main theory, we talked about viscous forces. And now viscosity, when it increases, this force increases, which causes smaller Reynolds numbers. And this means that the fingers will grow outward even more and even complexer. Okay. So we can predict that in more viscous environments, it will be faster and more complex and more unstable.
Okay, so can you turn to the page that you mentioned the viscosity of each stage?
Yes.
Yeah.
Oh, okay.
Okay. So each time, so the first drop up. Okay. So did you consider the water to acrylic paints like a portion as a parameter?
This portion is a parameter since I did pure acrylics 1-to-1 and pure water.
Okay. So did you have the pure water one?
I said because the diffusion barely happens.
Okay.
Yes.
Also. Okay. So can you define just briefly define what's fingering in your opinion?
So we can define fingers with let's say okay, this figure here. So we can see that as I talked about main fingers, what I said was this is like a main finger. Since we can see the outer circle right here, this smooth line right here. Okay, so the first and the widest part, that is the finger coming out, is the main finger.
Yeah.
And it will branch out. So the more branches it has, the more complex it will be. So after this, the fingers will become more complex, and then we define these as branches.
Okay, so So you mentioned branching out, right?
Yes, branching
So
out.
do you think that it would stop at some point, or it would infinitely?
It will, in physics term, there is no complete stop.
Yeah.
So we do think that this is a very, it will have a very, very minor increase throughout time.
Yeah.
But through, even through the microscope, as we saw, we can define it either by it's not expanding a lot in a short period of time, or we can use tracker to define its stop.
Okay,
So like here you can see that the velocity comes to almost a zero.
okay, so please can you like here? Can you? So I want to know how do you like analyze the finger?
How do I analyze
Yeah,
it?
analyze.
So by using tracker, we can track, let's say, 1 in 4. So here, I put the tracker tracking spot right here, and we put the video frames one by one, and we track this tip of the finger. So we mainly focus on this main finger and the tip of the main finger.
Okay.
Yes.
So you track different growth of the. You analyze different growth from the different branches. Is your opinion right?
We analyze the main fingers to be concise.
Okay. Yeah. Okay. Okay. So can you please turn to page 7.
Page 7. Okay.
Okay. So can you briefly define what is a Koch curve?
Oh, I said it looks like a Koch curve because this gets even more complicated throughout.
Okay. So I just so like is that the part that I previously mentioned that it wouldn't have a you mentioned that it wouldn't have a clear stop.
Yes, because for Koch curves, as n approaches infinity, the changes will become so minor that it isn't really that necessary to consider. But there will be still minor changes throughout. Yes.
So please turn to page 20.
Okay. Sorry.
So what in your opinion causes the instability?
So instability is caused by what I said, the Hill-Shaw flow. So you can see that small Reynolds numbers and miscible solution. This miscible solution because this causes instability because the different let's say liquids or fluids will have what do you call it? Like they have stuff with each other. Yes.
Okay. So okay. So the Hill-Shaw flow. How so what causes so let me change the question. How do you what do you think causes the Hill-Shaw flow?
Oh, the Hill-Shaw flow is caused by the fluid being very, very viscous and causing it to have, let's say, so a viscous flow. It mainly is a viscous dominant flow. Let's say that.
Okay, so in your opinion, does a different viscosity cause the instability that I agree with?
Yes, because different viscosity causes different viscous forces, and viscous forces causes the Reynolds numbers and the Hill-Shaw flow to differ, and
okay.
Yes, causing instability to change.
Okay, so yeah. Okay. So can you please turn to page 18?
18.
So what I previously wanted to ask is that can you define the red part, but I don't see it. So yeah, thanks. Okay, so page 36.
36.
So the definition of the final states is that if the tracker doesn't move anymore, it's
Yeah, so basically if like the velocity is coming to like, well, we defined it as the velocity decreasing to, we put centimeters per second, so we define it as 0.01 centimeters per second. So below that is a stop work.
So, yeah, can you turn back to the page that you were talking about, the airdrop?
Okay.
Okay, so as I've really previously mentioned that the viscosity would, the different viscosity would cause the instability. And now, what in your opinion does the different surface tension cause?
Different surface tension.
Yeah, different surface tension between different fluids.
And then can you tell me briefly about the ink alcohol mixture and the acrylic paints surface tension difference?
Okay,
for me to use it in my theory.
Okay, so I use it for.
Okay.
But that briefly, yeah, this is the paint. This is the fluid. So yeah, the difference of attention is that
We can have further discussion.
Yeah.
Come here, sir.
Thank you. Okay.
Upon a summarize the discussion, 1 minute.
Okay, so the first thing I asked is that can you define the fractal? And in his presentation, he did define the fractal. Is that so he defined that there are different branches, and the fractal from the stage 2 branches out, and that means a fractal. And if it didn't like, it's not it's fairly observable. It would, in their opinion, it would stop. So, and the second question I ask is that did you control your temperature and humidity? And these I mentioned about that the reporter did that. So I think it's a good part about their experiment. Yeah. So thanks.
Okay, time's up. Okay. Let's move on to the question of the reviewer to the reporter and opponent. 3 minutes.
Thanks for your discussion. So first of all, I want to ask you, do you know that alcohol is actually a polar solvent? Alcohol is actually a polar solvent. So basically, it can fuse itself, the ink, and the acrylic into another liquid. Do you know that?
Yeah.
Yes, we do know that.
You do know that?
Yeah.
And okay, so did you consider it?
You should add the reporter.
I'm sorry.
Okay, so yes, I do know that alcohol will mix those two together, but for the experiment that we didn't consider it because we thought it was unnecessary to consider such a minor touch between the two surfaces.
So what kind of alcohol are you using? The ethanol or the
Ethanol.
alcohol? Okay, so you're using ethanol. And what do you think caused the deceleration of the generating of fingers?
Deceleration.
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 Yeah.
Oh. So the deceleration of the fingers is because the more ink or the more flux it made outward, the less ink it had, or the less force it will still have. So that kind of meant that the fingers will eventually slow down.
So do you think it will stop?
Like I said in the discussion, I don't think that it will come to a complete stop, but we did define a stop.
Fine. So you define a stop. And I want to ask you, you have mentioned about the instability, right?
Yes, I've mentioned instability. Yes.
So what kind of instabilities are you referring to? Since there are various instabilities that can contribute to this phenomenon.
Let's say this instability is where's my instability? Okay, so instability here is when we have this line here, we see under the microscope that this is actually jagged. So our instability here is talking about this.
Do you have a specific name for the instability?
Specific name.
Yeah, it's like As far as I know, the segment Taylor instability often combines with the heel shuffle. So are you referring to the segment Taylor instability?
I'm sorry, say fun.
And so basically there are various instability, and do you what kind of instability do you think he's talking about?
So
Yeah,
I think in the presentation he's talking about like there are it looks like it's a pretty curve, but in the actual it would be like this graph. So I think the instability that he's talking about is this.
And I want to ask about this one. Are you referring to the mountain drop? The mountain drop like from here, or you're talking about here?
I'm talking about when it is more curved throughout the outer circle.
So
Okay, time's up.
Thank you.
Preparation of the reviewer, 2 minutes. Okay, time's up. The reviewer takes the floor for 4 minutes.
Good afternoon, dear judges, my partners, and my opponent, and my competitors. My name is William, and I'm from team WN. Today, the topic I'm going to review is question number 1, fractal fingers. So, please wait a second, sorry. So we think the main focus should be on the ink, alcohol mixture, and acrylic, acrylic paint, and also the geometry and the dynamics. So overview of the reporter, his advantage include the fair explanation of the phenomena, and observation video is of good quality, and also he considered the Reynolds number, and he also considered the heel shuffle, and he also reported the velocity data, which is substantial. And the suggestion for him include, he did explain how the heel shells characteristic of a microwave in a narrow gap work in this system. And also his lack of various parameters that the problem asks us to do so. And also he did explain which instability he is referring to, since the fingers can be contributed by various instabilities. For example, the Safeman-Taylor instabilities that usually comes with heel shell, which is an unstable displacement. That's led by the viscosity. And also, the calculation he used of the numbers of the fingers is not precise enough. And the time management of them can also be improved. And also, he should have used more precise dripping equipment like micropipette. Overview of the opponent, his advantage include he asks detailed questions about the experiments, and he also asks thoughtful questions that he has his own opinions on. And the suggestion for him includes could have the questions more well arranged. And also the graph he drawn there is not precise, since as we know there is fusion, so the interface will not be flat. And in terms of the discussion, the opponent first mentioned did you control temperature and humidity? The reporter answers yes, he did. And the complicated environment he was referring to is now the surrounding environment. And the opponent asked about the qualitative explanation. And the reporter mentioned it can be only predicted by experiments. And next, the opponent asked, how did viscosity affect? The reporter answers, when in a more viscous status, the more complex. And also, the opponent wants to discuss about how to define fingers. The reporter answers, the first come out cause the main fingers. However, the reverse things is not precise enough. And then, the opponent asks about how to define the stop of the fingers. The reporter answers, he will use the tracker to track its tip to define how is it stop or not. And he also asks about how to track different fingers. The reporter answers, he will check the main 5 fingers. And the opponent keeps saying that to explain the Koch curve. The reporter answers, the finger in the periphery will be minor. So this is why he cited the Koch curve. And the opponent asks, is a Hill shuffle caused by viscosity? The reporter answers, yes, and it will also affect the number. So conclusion of the reviewer, we think that the chemical reaction, like fusing of the 3 liquid, should be also mentioned, since alcohol in this experiment is a polar solvent. And can also affect the solubility and interfacial tension. And the reviewer thinks the cause of fractal fingers is various instability in the system that happens to generate similar shapes. And the reviewer thinks that the cause for the deceleration of the boring fingers is the growing of curvature that the reporter just talked about.
Okay.
Thank you for listening.
Okay, thank you. So, concluding remark of the reporter for 2 minutes.
So first, in my presentation, I talked about theories which were Hill-Shaw flow, Reynolds numbers, and the quotient growth, and also the positive feedback. And these are causing what I said, instability and the more complex the fingers will get. And the parameters I discussed were the viscosity and ratio of paint and water. So in my experiment, I changed the ratio of ink and alcohol, and also compared the finger with different initial widths, and also changed the ratio. So for the suggestions that the opponent and the reviewer gave me, I think that I can do a better job on making the experiments maybe more precise, and also to regard the reviewer's point of view on how I define the fingers. I would say that my method is good enough for my experiment at this level, but if you have a better suggestion, then can you please quantize it and tell it to me, please. And also, I'll thank the opponent and the reviewer for your recommendations. Thank you.
Okay, thank you. For last part is the question of review. Any question?
Okay, I have a question about the surface tension, because the reviewer and the opponent also mentioned about these issues. How do you think every time you do an experiment, I don't know how many times you do the experiment, because when you take the picture, maybe the second time you change your this other side, I don't know, because between the liquid and the surface referred by many variables. Can you mention about this? Do you know why? Ink, alcohol onto the plate. Yes. It is an interface, right?
It contacts.
Yes. So you mentioned the surface tension. Therefore, this problem. Can you mention something about it?
So for the surface tension, we didn't involve this parts of discussion in our experiments. But as a reporter, I do think that the surface tension will also be an effect in some point of the process.
Any more questions?
A simple question on the report. Why 3 drops? Can we just get by with 1 drop?
Oh, I said I experimented with 1 drop, but for the observation video, I wanted to make it clear, so I put 3 drops. Yes.
So you think 3 drops make it clear? 1 drop.
What I said was the observation video. I wanted to make it so that we can show fingers growing at a rate that the naked eye can observe. So we dropped 1 drop and then showed part of the faster growing, and then another drop to show.
My question is why you have to use 3 drops? Why can't you do 3 experiments each time with 1 drop? Any specific reason?
You mean for the observation video?
I mean, your video, you drop 3 drops.
times, yes. Yes.
That's my question.
I don't really have an answer for why I dropped 3 drops instead of 3 experiments with 1. And I wanted to say that I just wanted to make the video more observable through the naked eye.
Any more questions?
You mentioned the viscosity will affect your pattern, right?
Yes.
And I didn't see any new experimental about the viscosity.
I changed the ratio of acrylic paint and water. So when I use pure acrylic paint, the viscosity is the largest, and then comparing to water would be the lowest, and the 1-to-1 would be in the middle. So I changed my viscosity. Yeah.
So you can conclude the viscosity increase and the pattern will be.
More complex because the Reynolds number will decrease.
But if you more increase the viscosity, what will be happening?
The pattern of the fingers will get even more complex due to more instability.
The same question to you. Can you answer the question?
Okay, so the viscosity difference. I think the reporter did not mention in the presentation, so I talked about it, and I wanted to get his opinion about it. Yeah. So that's why I talked about it. And in my opinion about the viscosity difference is that so the different viscosity would cause the instability. So yeah.
My question is, if the viscosity increase a lot, what will be happening?
Oh, see. So which ones is viscosity? Like so
the
it,
will, what will you see the phenomenon?
So if the viscosity differentiate a lot, I think it would have a the velocity of the stage 1 to stage 2 and stage 3 would be a lot faster.
So if the viscosity increase a lot, can you still can see the finger?
So
the finger pattern will happen or just disappear.
so which viscosity are you talking about? Can you
Increase a lot of viscosity.
which?
I think the further means the
Acrylic paint. Oh, so so I think the differentiate of the I think the fingers will still appear.
I think the fingers will still appear. And I think if the difference between viscosity is a lot, I think the heel shot flow will increase. Because the definition of the heel shot flow is the one liquid with a lower viscosity will displace the one with a higher viscosity. Yeah, so I think this is why probably the velocity difference between the acrylic base is when its reaches higher and the reaches lower.
Okay, so let's finish this round and please take a score. So please show the score of reported. Okay, 7, 6, 6, 7, 8. And please show the score of opponent. 7, 6, 6, 6, 8. And please show the score of reviewer. 6, 6, 6, 7, and 8. Yeah. So, any comment or suggestion for the 3 teams? About the viscosity or something? Yeah. For the three shots. Yeah. Okay.
我讲的那个明知度的增加的话，你整个容易的明知度增加，其实到时候你的 finger pattern 其实不会出现。
没有哦，可是我不知道你在讲哪个年度，哪个。
所以换我讲就是那个。
所以acrylic 的
对
啊对。
对，所以你们3个都答错了。
How about the 3 drop or 1 drop?
我只是好奇为什么要 3 drops？ 如果是我就做3次。
因为就是它，我们是用滴滴管滴，所以第一滴它的液滴量是很少量的，所以它要展开，像我们到 stage 1的时候，它只能长出一点点的数字，我们还要再补充更多的液体量去，就是去，才能让我们的 observation video 能够看得清楚。
对，因为我会有类似的好奇，应该就3D 就一起滴对。不过你如果可以讲得更清楚，会更好。
你是第3倍。
对啊。哦。或是有什么目的这样？好，那我们这一轮就到这边。好，那我们要休息10分钟。
是我们提交大概20秒。没有。没有什么。
还是3个月多吗？
Okay, so everyone is yeah. So we will start our final stage. So the last one, the last quarter is CYJ, and they will report the problem 6, magnetic mechanical oscillator, and the please write down the name on the blackboard, and then start our timer. Thank you. Okay, thumbs up. Please start your report.
Okay, honorable juries and fellow competitors, this is the reporter from Team CYJ and my name is Brian Hu. Today I'm going to report on problem number 6, magnetic mechanical oscillator. So this is a problem statement. Secure the lower ends of two identical leaf springs to a non-magnetic base and attach magnets to the upper ends such that they repel and are free to move. And our main focus are investigate how the movement of these springs depends on relevant parameters. So here is the outline. The first, we are going to talk about observational experiment. The second we're going to talk about is the theory explanation, like normal mode and peak frequency. The third thing we're going to talk about is experiment stat analysis. We're going to talk about frequency analysis and Fourier transformation, and the conclusion. Okay, so the first observation is a preliminary experiment. So as you can see in the video, that the oscillation amplitude will change through time, and the energy seems like to transform between two horizontal spring oscillation. And you can see like there are two transform. three transform right in the graph. So I'm gonna explain the normal mode now. The normal mode is the mode moved as sine functions with the same frequency and phase. So it would look kind of like this. So here we're gonna explain the beat frequency. We put the y equals cosine 9x and y equals cosine 10x, and we put it together, it would look like this. And now it can look like this. So yeah, this is the full transform. And the beat frequency we can use fast Fourier transform to take this to transform into this. And this is normal mode frequencies. Now we're gonna explain the coupling oscillator. So as you can see, the coupling oscillator means that if one oscillates and it affected the other, and it oscillates too. So the coupling oscillation system, when it's spring and it's compacted with elastic bands. So when two such systems are close together, they form a coupled oscillatory system. And we can write two equations from this. So this is an equation of motion for the spring. After solving the equation, we can get the general solution of the coupling system. And it would look like this. By solving the solution, the value for the normal mode frequencies can be written as this and this. And you can see the graph here. And the discussion here. Because a completely linear spring does not match our experimental results, we changed the elastic force to use cylindrical magnetic force for the simulation. And it would change like this. So we can rewrite our equation of motion because we changed it to the magnet. And here is the main difference from the spring. So next, we're going to talk about the damping. We assume that zeta equals b over 2 kilometers squared. This motion is a kind of damping motion, and our experiment is under damping. So we will do the fitting in the next part. So here are our setups. We use a tracker to analyze the movement of the motion, and Python to plot the graphs and perform Fourier transform, and Desmos to calculate the variables. So here are our first simulation. So the spring would look like this. If we put our equation of motion into the Python, and the magnet part would look like this. And if we put a fast Fourier transform into, it would look like this. And so here we can talk about the symmetric mode and anti-symmetric mode. And the motion will be like two independent oscillators, so there will be no beat frequencies. And it would move like this. So first we can talk about the symmetric mode. You can see that, and as we use a fast Fourier transform, it would look like this. And the anti-symmetric mode, and it would look like this. So we can know that so we can compare symmetric, anti-symmetric, and coupled oscillations. When the initial conditions was closer to the normal mode case, the motion will be closer to two simple harmonic motions, and verifies that the combined motion of the oscillator is the superposition of the two normal modes. So here we talk about the experiment. So the experiment would change our displacement. So the parameters are displacement for the right side. They are equals to 1 and 1.5 and 2 centimeters. So the measurement we want to measure is the movement and the frequencies. And the control variables are the mass of the magnets, elastic coefficient of the leaf spring, and pole strength of the electromagnet, and the distance between two magnets. So here we are analyzing the 1 centimeter. And this is 1.5 centimeters. And this is 2 centimeters. So the frequencies will remain unaffected by the displacement we apply to the spring, but only the amplitude will be affected. So next, our experiment is about elastic coefficient. The parameter we use is the elastic coefficient. And the measurement we want to measure is the movement and frequencies. And the control variables are first, the mass of the magnet, and second, displacement of the lead spring, and third, pole strength of the electromagnet, and the distance, fourth distance between two magnets. And how do we change the elastic coefficient? Is by controlling the length of these poles, the spring. So we can change the elastic coefficient as, yeah. So first, it's the motion analysis of the 8. When the elastic coefficient equals to 8, we would get this motion. And when the elastic coefficient equals to 25, we can get this graph. And when the elastic coefficient equals to 37.5, we can get this graph. And when the elastic coefficient equals to 125, we can get these graphs. Okay, so the conclusion are, as the elastic coefficient increases, so do the frequencies. But if the coefficient becomes large enough, the coupling effect may become difficult to observe. And we can compare it here. So next experiment is about mass. So the parameter is the mass of the upper part of the lead spring. And the measurement we want to measure is the movement and frequencies. And the control variables are elastic coefficient, which is 25, and the displacement of the lead spring, pole strength of the electromagnet, and distance between two magnets, and the displacement of the spring. So if we add 2 grams onto the lead spring, it would look like this. If we add 4 grams onto the lead spring, it would look like this. If we add 6 grams onto the lead spring, it will look like this. And the conclusion are, according to this result, as the mass on the magnet increases, the frequency will also increase. So we can compare our results in here. So we can see the difference. So we're going to talk about the conclusion. So when the initial conditions are closer to the normal mode case, the motion will be closer to 2 single simple harmonic motions. And verifies that the combined motion of the oscillator is the superposition of the 2 normal modes. And we can compare the symmetric mode, anti-symmetric mode, and couple mode in here with their Fourier transform graph. The frequencies will remain unaffected by the displacement we apply to the spring, but only the amplitude will be affected. And we compare our results from here. And the conclusion, as the elastic coefficient increases, so do the frequencies. But if the coefficient becomes large enough, the coupling effect may become difficult to observe. And we can compare the experiment results in here. And this is a graph for Fourier transform, and this is a graph of the track. So the conclusion. According to the results, as the mass on the magnet increases, the frequency will also increases. So we can compare our experiment results in this page. And this is a graph for Fourier transform, and this is a graph for the track. So the first conclusion, when the normal mode frequency are closer, here are the written down, the coupling effect will be better because of the K and the omega effect. So the second, the alternate frequency equals to the difference of the 2 frequencies of the normal mode. So we can write it down as omega 1 minus omega 2 equals to omega b equals to the alternate frequency. Right here. And third, the initial conditions will not only alter the amplitude, but also change the coupling phenomenon. and coupling that provides only the right spring is better than providing both sides. Adding more mass on the system would make the normal mode frequencies get smaller. Thanks for listening.
Question about opponents to the reporter. 2 minutes.
My first question is that does the recovery force will be proportional to the space that you pull the magnet?
Can you rephrase the question?
Will the recovery force be proportional to the how much you pull the magnets?
We didn't calculate this, but I think it will be proportional to the recovery force.
What about the magnetic force? Will the magnetic force be proportional to the space between the two magnets?
Sorry, can you?
Like, will the magnetic force be proportional to the space between the two magnets?
Oh yeah.
Yes. And what do you think is the main cause of damping?
Okay, so the main cause of damping, we think is that the friction, like the air condition, the air restriction.
So you think it's the air restriction?
Yeah.
Air force?
Yeah.
Oh, cool.
And the energy transform between two magnets.
And in your videos, we can see that your damping is actually quite fast. Not in videos, like in your gas. In your gas. Your damping is actually quite fast. Why is that? What do you think is the reason of that?
Maybe it's because our experimental data, it would look like this.
Okay. How do you define did you define the center of mass in every of your experiments?
No, we didn't define it.
Okay, I have another question.
Okay. Preparation of opponent, 3 minutes. Okay, thank you, sir.
Good afternoon, esteemed judges and fellow debaters. My name is Sherry Gao, and I will be opposing for problem 6, magnetic mechanical oscillator. So the problem statement was secure the lower ends to two identical lead strings to a non-magnetic space and attach magnets to the upper ends such that they repel and are free to move. Investigate how the movement of the strings depends on relevant parameters. And they focus on how the movement of the strings by relevant parameters. And their theory is that the energy seems to be transforming, and then the coupling oscillator system and the equation of motion for the spring, and the equation of motion for the magnet, and also damping. And their setup was that they used the tracker for analysis, they used the Python to simulate, and Desmos for the Fourier. And they also used the Fourier transformation and magnets and oscillator. Some conditions, the parameters was that they displaced for the right side, and they use elastic coefficients, and they add mass to the string. And the analysis was that they analyzed the relation between parameters and the frequencies and amplitudes. So their conclusion was that the amplitude will be affected by the displacements, which frequencies will not. And the frequencies increases as the elastic coefficient increases, and it's harder to observe coupling effects. And the more mass added, the more the frequency will increase. And the initial condition will not only alter the amplitude. Their advantages was that they had various graphs that are clear and done well. But our suggestion was that some words on their slides aren't clear enough, and they could have done more experiments, and they had or have some error bars, and they could have focused more on magnetic force and damping. So these are my points of discussions, and I would like to start my questions.
Okay, we will start a discussion.
In my short questions, I asked you if the recovery force is proportional to the how much you pull the magnet.
Yeah.
But you said you were not sure, but it was supposed to be, you should have done like an experiment to explain this, because if you were not sure, then you cannot use...
I didn't say that I'm not sure, but we didn't calculate it if it's proportional to it, but yes.
Yes, exactly, so you don't know if your experiment is proportional. Am I correct?
Yes.
Yes. So when you're trying to say, oh, stop right here. Like last page, last page, last page, last page, last page. Like yes. So when you're trying to use the springs to explain your recovery force, then this model will not fit in if it's not proportional. And it might not be proportional. It's because that it might the rulers that you're using might not be a rigid body, and then so the k is different, and when it's not
K
proportional.
so k is one of our parameters here. So we control k as the same.
Yeah. But if it's not proportional, then even if when you're you control k, then your experiments will be inaccurate.
Okay.
And that would be one of the suggestions that you should try to see if the amplitude would be proportional.
Okay.
And the next short questions that I asked you was that the magnetic force should be proportional to the distance between the magnets, right?
Yeah.
And you said sure. But in page 10. In page 10, this thing, you're showing that the magnetic force will be sort of close to x to the square, but this doesn't seem that it will be proportional. This doesn't look like it will be proportional.
So I think I didn't listen to your questions clearly, but can you repeat your questions? Yeah.
I'll go slower. I'm sorry.
Sorry.
When I asked you if the magnetic force will be proportional to distance between the.
Oh, so yeah, it's not proportional. It would be like the square or the fourth square. Yeah.
Well, but if it is not proportional, then you cannot put it into your this movement like that.
Yeah.
A spring model, because
so this part I was just talking about, like then if what no beating would look like. So this is the symmetric mode and this is an anti-symmetric mode. Yeah.
Yes,
so it doesn't. It's
your theory is based on your like you put different your parameters into this spring model, right?
Yeah.
Like the recovery force. Yeah.
No, but we didn't use spring model to decide the effect. We use the magnetic model to use the effect. Yeah. So
well, when you're trying to fit your magnetic model into the spring model, you fix this, but that would like show your omega thing. Well, omega equals to m divided by k divided by m.
Where?
One of your pages I forgot to. Oh, so omega squared is equal to k divided by m, or like k plus 2k prime divided by m. But when you're trying to use spring model to explain this doesn't work.
Yeah. So we were just talking about the equation of motion of the spring. So we're just talking about the equation of motion for the spring, but we use the equation of motion of magnet to use it fit it in our experiment. Yeah.
Well, what's the point of showing that model then?
Just because we mentioned that the coupling oscillation is mainly using spring, but in our experiment it's like we're using magnets, so we want to compare it together. So if it's the difference.
So it's just a comparison.
Yeah, just show the difference. We're just showing the difference. Yeah.
So then, in your if it's not in your theory, then what does the omega equal to?
So in my theory, I think it was.
You're trying to compare, right? It's a comparison. So in your theory, what does the omega equal to?
The omega equals to the velocity of a I mentioned.
But like an equation.
Oh yeah. So here, so the omega here equals to like.
So
it's a function. This is a function, but.
I just want to know the omega in your experiments. What does that mean?
And we're just showing like the derivation of the formula. So we use this.
So what's the meaning of this comparison? Like this page and the next page.
So the discussion is that we use this. We want to compare the spring and the magnetic model.
Yeah, but the comparison, like, what's the meaning of it?
Because we previously mentioned that the coupling oscillator
Well,
we use this.
Since this is like irrelevant to your thing, then why are you trying to compare this?
So like it's the thought process. So it's about like we first use this the
so
coupling
this is your thought process.
Kind of this about, but we wanted to show it and because we use this coupling oscillator to compare it to our experiment, because we think that it's similar to the coupling oscillation which uses the spring.
Well, then you failed to use your theory to
but the theory here
of your thing.
Okay.
Yeah, that would be something that we maybe want to work on in the future. And also in my short questions, I asked you that you believe that the Air Force would be the most will be the most major thing.
No, not the most major thing. I think the energy transform and the energy loss between the transform would be the major thing that causes decay.
Can you calculate the energy loss or something?
We didn't calculate it, but we can calculate it in the future work.
Yes, it's because you don't have the damping coefficient, which maybe you would also want to work on in the future. About the error bars I mentioned, like you must have some errors in your slide because if we would move to the one that you added mass on.
Okay, here.
Added mass.
Here. Yeah. Right.
Yeah. Then when you add mass onto it, does that mean that you are changing the center of mass?
Yes.
Then will the center of mass changing will affect your experiment?
Yes.
Yes, but you didn't do any like errors like to fit this. So
Okay.
maybe that would also be something that you want to work on. You said that there were damping indirect effects, but you don't have like any damping experiment data on this. Like how much is everything? You didn't quantify it. You didn't quantify
Yeah, we didn't quantify it, but we see it in our graph. So,
yeah, you only know that it's damping, but you don't know how much it is in every second.
So the motion is kind of damping motion, and our experiment is under damping.
Yeah. But you're trying to fit in.
Yeah.
But what are you trying to fit in? You must be like trying to fit in some kind of coefficient or something, but you're not showing any like damping coefficient to me. So, which should probably be something that you still want to work on.
Yeah.
The one that this when you pulled both.
Yeah, I know.
Why do you think that there will still be two peaks in the Fourier transformation?
Just one peak.
But just one peak, so what's that?
So which one?
Next page.
Next page.
Next page.
This is a couple.
No. When this thing. Oh yeah, this.
Yeah.
Why do you think that there will be two peaks? Like there's still like.
So this is. Do you mean a small peak here?
Yeah.
So I think this is because like this symmetric is not fully symmetric because you can see that they are still like not.
So like, why do you think this is not fully symmetric?
Because it may be affected by the environmental issue. But,
will there be a possibility
yeah.
that it's because you use your hands to pull them?
Okay.
So this was not so precise.
Okay.
And yeah, so this is something that you would also want to work on to make your data more precise. Since you didn't put any like error bars to your thing, so yeah. So this is like imprecise either. And in your conclusions, you said that when the mass of when you add mass, and then the frequency also goes up. But I think that I don't see this tendency.
You mean so here. So the
how does the frequency go up? It's actually going down. The amplitude is going up, but the frequency is actually going down. Like in every single peak, it's actually going down, right?
No, it's not going down because like it's
the
going up.
frequency, yes, that's the amplitude, but the frequency is going down.
Yeah, so
but in your conclusion, you said that when you add mass, the frequency goes up. So this is another error?
Yeah. Yes.
Yeah. So maybe you want to do more on that too. And then thank you. My time is up.
Thank you. So the opponent summarized the discussion for 1 minute.
In our first discussion, we talked about the rigid body and how that they should have done this to make sure it was proportional. And the reporter believed that yes, that may be something that they want to work on. And to make their experiments more precise, they should also consider the center of mass or their damping coefficient, and also what their point of what the omega meant. Yeah, and also they had to change one of their conclusions was that when the mass goes up, it's the amplitude that goes up, not the frequency that goes up. The amplitude goes up and the frequency goes down. that would be some the conclusion that they want to change. And what else? And that's probably it. And they shouldn't have used hands because that would be imprecise. Thank you.
Okay, let me start. Question of reviewer to reporter and the opponent.
Okay,
30
so-
minutes.
Hey. Okay, so here I want to ask the first reporter. So what do you think is the main parameter that affects the motion?
Okay, so the parameter that affects the motion is that the main parameter we use is that we change it the elastic coefficient, we change it to the mass, and we change it to the mass.
Okay, then.
The main one is the magnetic force changing.
Okay, then.
We believe so.
Okay, so in your left symmetric motion, you said there's some error. So it didn't really like the motion like this, but some shaking while the motion. So what do you think the source of error?
Maybe like using the hand or like the natural conditions. Yeah.
Okay, then opponents.
Because that's the initial conditions weren't like very precise because they use hands or something.
Okay, so like you said in your experimental result that you show the damping, right?
Yeah.
So where do you show in your theory?
So in the theory we didn't show that, but we can observe it in the graph.
Okay, so then in your graph that you define there's a 0 point, and then you analyze.
What do you mean the 0 point?
Like the axis here and here's the 0 point,
Oh,
but the two of the motion that you analyze, one is from here the positive and one is the negative. So where did you define the 0?
So like in the tracker we can analyze by putting like different like when we put like the axis on the point, when we track like we can have the different results on the x-axis. So like there will be positive and there will be negative.
Where?
So we put it on the tracking point that it's in our.
Okay, so next question. Do you consider magnet force in the theory, right?
Yes.
Yes. So since that just opponent said it's proportional to the distance between two magnets. So
Here, like we use this tracker. And
okay.
So we put the axis right there.
Okay, then sorry. Can you turn to the theory page? Let's show the result of your theory. Like
Yeah.
show. Yes. So like just okay. Okay, no. Then does the theory fulfill the experiment? Yes or no?
Yes, but it's only like the equation of motion of the magnet, and we did.
Okay, thumbs up.
Thanks.
Okay, preparation for reviewer for 2 minutes. Thumbs up.
Okay, so I'm a reviewer from Pink Chocolate Tea, and today I'm review problem number 6, mechanical oscillator, and I'm consumer. So first, the problem statement: secure the lower end of two identical lead springs to a non-magnetic base and attach magnets to the upper ends, such that they repel and are free to move. Investigate how the movement of the springs depends on relevant parameters. So here's pros and cons. The first reporters, pros is well introduction of phenomenon, separate theory considering, and good animation for phenomena understanding. Implanted flow simulates tools using and detailed experimental results. But the con is reading a presentation lacking precise experiment setup and hard understanding explanation of theoretic equations, and lacking parameters like air resistance, recovery force considering, and lack of explanation of graph, and no quantitative comparison between theory and experiment. So I don't know if the theory is perfectly fit the experiment. No, the experiment perfectly fit the theory. Okay, then the opponent approach is ask problems straightly and complete summary of reporter, well observation of graphs, and complete theory understanding. Having advice of reporter and putting out the reporter's mistakes, like didn't consider the distance between two magnets. Okay, then the cons is ask some questions having mentioned by the reporter, and that can deep problems. Mainly discuss error but lack detailed discussion of parameters and nonlinear damping act. The point I missed by both is first linear or nonlinear frequency fitting. Experimental data corresponds and air resistance put into the theory. So here's PF question. So first opponent's question is the cause of damping, and reporter's answer is air drag and energy transfers, and opponent reviewer also agreed with the reporter. Then the reason of the fast damping, the reporter's answer is their experimental data. And in our point of view, the reporter should be able to explain damping through theories. Then opponent's question, the recovery force proportional to magnet. So the reporter's answer is didn't calculate the force, but in our point of view, we agree with the opponent that recovery force should be considered to make the theoretical model accurate. Then opponent's question is where does the omega equal to in a theory? That the reporter didn't give a clear answer, and we agree with opponent that the theory is not used in the experiment. Okay, then the opponent's question is the decay of energy. The reporter's answer is we didn't calculate the damping coefficient. And in our point of view, the reporter does have to work on it to make the result persuasive. And opponent's question is does the change of the central mass affect experiment, and reporter's answer is yes. And we also agree with the opponent. And opponent's question is the two peaks in Fourier transform. And the reporter's answer is the small peak is because the experiment is not fully symmetric. Okay. Then reviewer's question. So first I ask the main parameters, and reporter's answer is magnetic force changing, and opponent has the same answer. Then I ask about the source of errors. The reporter's answer is natural conditions, unprecise experiment. And opponent's answer is unprecise experiment. And I ask where can damping be seen, and reporter's answer is only in experiment. Where is the original point to find? The reporter's answer is the tracking point. But I don't.
Thumbs up. Thank you.
Next.
Then, concluding remark for the reporter for 2 minutes.
So here are our concluding remarks. So the experiment part, we did the parameters. So the first parameter we did is the displacement of the lead, and the second one is the elastic coefficient. The third is the mass. So the discussion points are about damping, and so there are multiple discussion points. But so the one I want to mention is the damping. So we didn't calculate the damping coefficient, and we didn't calculate the exact number of the damping coefficient, and we think we should calculate that in our future work. And the discussion points, they are also, they talk about we're using hand, so they are not completely same in the symmetric mode. So we think we can change that into the more precise method. So the fixing part is to do the experiment more precisely, which I mentioned above. And second is that we should consider more factors that influence the theory and the experiment that need to be fit in the theory, yeah, etc. So thanks, that's all.
Okay. So that's a question or jury? Any question? Okay.
I have a question for three of you. How to make the strong couple condition in this system?
So first, I think we can add more magnetic force by changing different parameters. Like adding the magnetic force can have these strong.
So if you add the magnetic number, then what happens?
A magnetic number, but it will also change the mass of the lead. So we didn't do that experiment because it will change multiple parameters at one time.
Okay, and Ellen?
I believe that if two of the magnets are placed closer, then the oscillation will be more observable.
So I think the elastic constant of the difference is important because this is one of the force source that cause the couple motion.
Okay. Any question? Yeah.
I have a question. I'd like to start from our opponent and then the reporter and then reviewer. Right? You're asking this mode, right? Okay, so and you speculate that from the Fourier transform, you think the second peak also appeared.
I believe that it was.
Let me finish my question.
I'm sorry, I'm sorry.
And you speculate it's the not so well controlled. It's the main source. Okay, so my question is, suppose someone can do the experiment perfectly. Do you expect to see one peak or two peaks?
One peak.
Okay, how about you?
Yeah, also one peak because yeah.
Okay, one peak. Okay, thank you.
Any more question?
Can I see the page, two, one, two, three figures? No.
Three different modes.
Three different modes. Oh, here.
So,
Yeah.
this one.
Yeah.
Do you see, can I see clearly? Because the position of the first one cannot be fixed to the right figures. I don't know how. Because this number on your x-axis is too small.
Oh.
Yeah.
So this is
If the two figures is the two modes, it will consist of the combination of the two modes. So the position cannot be altered. I don't know.
So the you mean the
Yes.
number?
Not this one.
Not
Because
The symmetry in the
yeah.
only this picture. Yes. This one is a symmetry, right?
And anti-symmetry.
1.75. Maybe it's okay. So the other one.
The previous one.
Yeah. This one. 1.3. Yeah. So these two normal frequency will occur in these two big. I don't know. I can observe very clearly when the white figures in the three. I don't know. It is the same.
Which one do you?
Not this one. Three figures.
Oh.
Three figures. Three. This one.
Oh, this one.
The white one.
position of
The position is not correct, I think.
Oh.
So what happens? I don't know.
Maybe like I think we used I think the coupling oscillation was not the same model with these two.
Can you change to 24?
Okay, okay.
Yes. So what is the whole strength of the electromagnetic? Where you can find electromagnetic?
Electromagnet is right here. Like,
So you use the electromagnet.
Is that the magnet or the electromagnet? Did you?
oh,
Yeah.
it's
Any
the
current?
magnet.
Yeah, in the
Yeah,
magnet.
it's the magnet.
So I think you make a mistake.
Oh yeah.
Right hole.
Yeah.
Yeah, thank you. So time is up. Yeah, please calculate the score. Okay, yeah, so please show the score of reported. 6, 8, 5, 6, 7. Yeah, and the score of opponent. 7, 8, 7, 7, and 7. And the reviewer. 6, 7, 6, 6, 7. Yeah, so operation, we just finished our round. So, yeah, so any comment or suggestion for these students? Yeah.
补充好，就是说刚刚有3个，那个答案是它不会是，因为你这个系统就不是线性，这是为什么你3张图那个你看否的跟原来不一样，因为那magnetic force 是非常。
对，不是对，它应该是一个2次方的比。
对，就是你那个 normal mode 假设是线性的时候，那它就会对。但是因为它的 magnetic force 就不是线性，所以你不会看到它。
对，所以2个教授题就兜起来，对我觉得奇怪。那所以它不一样，应该是合理的啦。
对，它本来就不应该。
对啊，你要搞清楚，对，要确认，对。
对。所以你选用 normal mode 也是一个好的出发点。
建议大家录影片制作的时候要漂亮一点，你的图要清楚，你的字跟 background 的颜色要对比到很强烈，就是你的 background 越暗的颜色，你的字要越淡的，不然这个颜色。
这个评审能力就有点大，这个字太小，就没有办法。好，我先了解一下你们其他的数据。